All right, good morning, everybody. We did our project on hydrophobic paper straws, and I'm Sangeeta.
I'm Adam.
I'm Natasha. I'm Vivi.
I'm Ian.
And this is our project.
So what inspired our project is that today there's been this huge public uproar about plastic straws hurting the turtles and destroying marine life. It's been this whole thing. So as an alternative, people have used paper straws, but those aren't much better either. They get really soggy over time. They break down, and they're just not really that good at all. And you often need like more than one paper straw for like one drink. And so, some vocabulary we'll need to know before we get into the bulk of our project. Thank you. Is surface wettability. That's the degree to which water will adhere to a surface. High wettability being when water adheres really well, and it would be really hydrophilic. And low wettability when water doesn't adhere to a surface very well, which is hydrophobic. And the last term we're going to need to know is nanoroughness, which are really small pillar structures on the nanoscale, which is 1/1000th of a meter, so times 10 to the -9 if you know anything about that. And they have really high surface area. And so our driving question for our research was, how can we create a hydrophobic paper straw that's both non-toxic and biodegradable? And our hypothesis is that if we can cap this titanium dioxide solution in oleic acid, then a nanorough and hydrophobic surface will be able to be created, and we can save the turtles.
So here's how we designed our experiment. First, we prepared captured oleic acid and titanium dioxide nanoparticle solution. And the way we do that is we first weighted the chemicals and we added acetic acid to the mortar. And as you can see in the top right picture, we're grinding it up for at least 25 minutes. And the reason we are grinding it up is because even though the TiO2 chemicals can seem to be really small, they're still at a micro scale, which is 10 to the -6. But then, as Ian said, nanoscale is 10 to the -9. So even though it seems like there's not of a big difference, there is, because the smaller the particle is, the more surface area there is. And they have the unique physical features that we can take advantage of. And then after that, we added oleic acid in order to cap the particles from getting too big and lose those features that we wanted to have. After that, we coated our straws with the TiO2 solution we made, like the picture shows, and after that we allowed the straws to dry for at least 30 minutes. So here are just two GIFs that shows how the hydrophobicity works. So as you can see on the left side, that's the regular paper straw, so we didn't do anything to it. And when you drop water on it, you can clearly see that there's still some water that are attached to the straw, which makes it soggy after a while. But on the right side, you can see after we dropped a water droplet on it, it didn't stick to the straw at all. It dropped off, which makes it less soggy after a while.
Okay, so just to, again, verify hydrophobicity, so we dropped a water droplet onto our straw and measured the contact angle, and we measured it to be about 140 degrees. And basically, if the angle is greater than 90 and less than 150, it is considered hydrophobic. And then for our last step, we tested the properties of the straws by soaking them in water or weighing them. And basically, all of our testing is we tested durability by weighing them with pennies over here. So you can see in between the two tables, we laid our straw. And then we had like a little basket full of pennies that we dropped into. And then until the straw broke, that's how we measured durability. And then we also soaked them in water for different increments of time. And we tested the durability after soaking. And then we also tested them in different liquids. So we did Coca-Cola, and then boiling water, and then ice water. And then lastly, we stirred the paper straw and then our coated straw at a constant speed and to see which one would bend first.
I'm going to take a closer look at the actual durability testing. So here we see that there is this straw, and we made some sort of basket contraption and placed pennies into it, and we have the weight of the pennies and the weight of the basket, and that pretty much tells us the amount of weight that this straw can handle, which in turn tells us the durability. So using this testing technique, we got this data, and we pretty much see that paper straws and coated straws here both have a very similar durability, from 10 minutes soaked in water to 30 minutes soaked in water. However, after 30 minutes, leading up to an hour, we see that the durability of the paper straw starts to decrease, while the coated straw has a constant durability, which suggests that the coated straw can likely stay stronger for longer. Similarly, here we soaked our coated and our non-coated straws in Coca-Cola, boiling water, and cold water, and we see that the different durabilities are very similar, which is congruent to what we saw here, where at 10 minutes the durability is really similar. So it's positive because it means that our coated straws can also handle different liquids and liquids at different temperatures.
So the coated straws, they take more time to bend than the or deteriorate than the paper straws while it's being stirred, because of the TiO2 and it's hydrophobic. The water, it does not absorb the paper straws. Yeah.
And so some trends that we found were that the TiO2 coated straws and the non-coated straws were pretty similar over short periods of time, but over long periods of time, the coated straws were overall stronger, but we could do more experiments to solidify those results. And some possible sources of error that could have affected our results could be that inconsistent straw length. So if you have a longer straw, it's going to hold less weight, and if it's a shorter straw, it's going to hold more weight. Because if you think about it like a crayon, if it's like your wax crayon and you keep breaking it in half, it gets harder to break in half over time, so a shorter straw would be more durable. And inconsistent straw overlay, so if it's unevenly placed, then it would hold less weight, but if it's evenly placed, then the weight distribution would have been better and it would hold more weight. And then the last thing that could have affected our results is that titanium dioxide by nature is really flaky. It's what's in white paint, so when it flakes, it makes micro cracks, and it takes away the nano features, which would make it more hydrophilic than hydrophobic, which would skew our results.
So for further research, we're going to have to find an alternative nanomaterial that's biodegradable, that sticks to the straw, and is non-toxic. And we also have to find, theoretically, all the chemicals that we put inside our straw are biodegradable, but we still have to check if the mixture of those chemicals is biodegradable itself. And around 5 to half an hour, the TiO2 straws have about the same durability of the paper straws. But afterwards, the coated straws are better than the paper straws, and while stirring, the TiO2 coated straws is twice as better than the paper straw.
Thank you for listening. Do you have any questions?
Yes.
Great presentation. Just two questions. One, maybe I missed it, what's the specific property of TiO2 and the oleic acid that allows this? And the second question is, how did you measure that angle, 140 degrees?
Have you seen this diagram? You have this TiO2 nanoparticle right here, and you have this oleic acid molecule. The oleic acid molecule has this little group on the end of it with a hydrogen. It bonds to this oxygen electrostatically, so they're bound to each other. So it creates this little shell around the nanoparticle, and then this end right here, it repels water because it's nonpolar.
And then to measure the contact angle. So basically, we took this picture flat on a surface, and then we used a protractor and lined it up right at that point, And then we used Protractor to measure the angle of the water and to see if it was super hydrophobic or hydrophilic or regularly hydrophobic. Any other questions? Yes.
Two questions. One is, did you look into any other material before you decide making the decision to use titanium oxide? And a second question is, how much would be the average cost for each straw if you make 1 million straws?
So to answer your first question,
We were planning on doing first silver oxide, but then we didn't have enough materials to make it, and so we didn't have enough time to make it. But that's as well in the further research. We might do that for different nanomaterial.
and we also planted to do silicon dioxide, which to create the nanoparticles, it was a very difficult process to make. And so we decided to do titanium dioxide instead, since that was just easier to do in the span of time that we had.
And then titanium dioxide is it's what gives white paint its like really white color. It's non-toxic, and since it's produced on the mass scale in the painting industry, I believe that it would be pretty cheap, although we don't know the specific cost.
It's also found in sunscreen.
Yeah.
Any other questions?
Okay, so this is a sort of thinking future. So the goal, so titanium dioxide, so the reason you're using the titanium dioxide is to make it nano rough, so you can try to make it super hydrophobic. But titanium dioxide is literally a rock. So it's not a plastic, but it's not biodegradable. So could you think about what you could do to make the same kind of structure that was entirely biodegradable?
We would probably use silicon dioxide because silicon dioxide it's basically just quartz. It's really abundant in the earth, so.
But it's also a rock. So it doesn't go away. I mean, titanium dioxide and silicon dioxide are both they're rocks. So yeah. that part's sort of not so bad in nature, but they don't go away. So what does it need to do to be actually biodegradable? And what could you possibly do to do that?
So if we had more time, we would probably try to research other materials that are such as plants, since plants are, certain plants have a hydrophobic surface. We would try to mimic that coating onto our straws, since that is also biodegradable. We didn't have enough time to obviously get that material, so for future research, that's what we would probably do.
Yeah, you didn't have anywhere near enough time, but if you could make nano rough out of paper and then make it super hydrophobic, it would still potentially not wet just because of its nano properties, even though it was fundamentally all cellulose. Okay, good job.